What's happening, everybody? Welcome to our science. Let's talk through this. I got to fill this part out with you right here, at the bottom of page 6. Quick shoot through everything else just to throw it out there. Give me the 3 definitions you did back when we started this whole adventure. They don't have to be sciencey sounding definitions. Do the ones we did in your lab book. Keep it simple so that they make sense rather than something that's full of vocab from the internet that we can't quite easily interpret. Over here, this really should just be copying right out of your lab book for this whole entire page. You're solving for porosity. We talked about what those two were. That's what you measured on that day. Here, you'll quickly tell me, how did you measure it? Physically talk through the procedure. A couple sentences. It shouldn't be much. We took a predetermined amount of water, dumped it in, blah, blah, blah. You tell me what you did. For this, you don't have to do any numbering, labeling, anything. This is going to be really just quickly tell me what the trend was. Like if it went up, 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 like that, that's fine. If it went down, 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 like that, that's fine. This lab is tough to get the data to work exactly right, so sometimes we get things that go up and down. If that's what you got, that's what you got. Give it to me. Just quickly sketch what you got there. And then do the same thing for permeability. Tell me how you got it. Check your numbers. Same thing for capillarity. Tell me you got to check your numbers, and you'll be good. All right, so here's the real graphs, but I know it looks like a lot, but don't panic. It's only 3 points per graph. The particle sizes are 4, 8, and 12, which is a typo in my lab. 4, 8, and 12. So at 4, what was your porosity? Put a button, dot. A bigger one than that, though. At 8, what was your porosity? And at 12, what was your porosity? Something like that. And then switch to a smaller one. Connect the 3 dots. And then switch to a smaller one. And you'll be good. Way better than that. You can do better than that. Because I'm just making these numbers up anyway, right? So do that. 3 dots per, 3 dots per, 3 dots per. Connect them. People flew right through it. No big deal. A couple questions for you. Now what we're going to have for these 2 sections. What were your results? And then here's how it should work. Now this lab is not perfect for many reasons. The equipment we use, the width of the tube is really the biggest thing because the beads touch the wall really more than they're contacting each other, which throws off what the permeability, porosity, and capillarity would be if it was just the beads. Maybe you hit your timer wrong. Maybe the little white thing was being a pain. Maybe some water spilled, plenty of water spilled. So I'm not looking for exactly perfect results here. They're very difficult to get. Nonetheless, I want you to give me your results here. Tell me, as particle size increased, what did your numbers say permeability did, and what did your numbers say capillarity did, and so on. Down here, here's how it should work. If this experiment worked perfectly, here are the things that we're looking for in real life. So permeability. As particle size increases, what happens to permeability? Now, permeability is the speed that the water would trickle through the particles. Here I've got bigger spaces, and there's less of them. So the water can really find an easier path and more quickly get through this because permeability is all about speed. This is a more slow process. Okay, so as particle size increases, the bigger ones, we get also an increase in permeability. Cool. Capillarity has to do with how much water is getting stuck to these particles. Which one between these 2 images looks like there's more available surface to get stuck on? Well, if you guess the small ones, you're right. The small ones do. The larger ones just have less available surface to grip to, whereas the smaller ones, there's more outside of each bead because the beads are smaller. So in this case, as particle size increases, and there's less and less and less available surface for the water to stick to, your capillarity will decrease. Lastly, porosity. This is the tricky one. What happens as particle size increases? Porosity is like the ratio of space to beads. I'm just going to get rid of these lines here. So I can see big spaces here, so that feels like it has a high porosity, but there's less of these big spaces. The spaces here are tiny, but there's more of them. And as it turns out, the ratio stays about the same when you're dealing with rounded and sorted particles. Porosity stays the same. Now, just zooming, if you can, this is kind of an abstract thing, but if you can consider this with zooming on this document is printed, right? It's a PDF. I'm not changing anything about the size of this document or about the ratio of beads to space, right? If I counted up all the space of the beads and all the space of the holes, but then go and make the lab bigger just with the zoom tool, I didn't change that ratio at all. This is still the same document. The beads look bigger now. I could say those are big beads. I could say those are small beads, but it's the same picture. The ratio of bead to space stays the same the whole time. Another silly example I sometimes use is if I gave this student 10 $1 bills, they'd have $10. If I give the other student 1,000 pennies, they'd also have $10. Less of a bigger thing, it can equal more of a smaller thing. All right, so porosity is a strange one. Did your numbers reflect that? That's really difficult to get to work. Maybe it did. Maybe we got lucky. We'll see how it goes. If it didn't, you're not going to lose points or anything. I want this to be accurately done for your data, not lying to try to make it match that. That doesn't matter. Excuse me. Then we'll think of particle sizes quick in terms of soils and aquifers. This will say in this paragraph in a couple of different places, color this layer of the diagram a specific color. So that's your job. You'll do that. And then we'll think about what might be good for drinking water, like with this one, or the confining layers is basically the opposite. What this lab showed us is that larger particles allow water to go through faster. In terms of soils, sand is a pretty coarse particle. You don't have soils made out of boulders. That doesn't make any sense, right? When you get down to what a soil is, having a lot of sand in it allows water to trickle through very fast. We have this at my house. We've got a lot of sand, and it allows our well to get pretty good water flow to it. We've got neighbors that don't have that body of sand near, which is a esker, if you remember glaciers, that are only clay, and that clay does not allow the water to flow towards those wells very easily. So if they turn on their faucet, it turns on the well and it sucks water out. How quickly can that water get through back to the head of the well? If it's a clay soil, it's a low permeability, it's very slow, and that's problematic. If you have a sandy soil, that's very fast, and that's good news. So that's the basics. You'll think about a couple of things, color some of that, answer those questions, and you're out of here. And congratulations. It's the last of the big, huge, heavy data, gather data and graphic kind of earth science labs. We move into a lot more like qualitative labs after this. So you've done it. Keep up the good work. I appreciate it. So long for now.